Welcome! This is the video tutorial series on the Roloc Pond construction technology presented by SCAT Rwanda and the ProEco program. Part 2. Roloc Pond structural design principles. In this video, we will have an overview of the structural design process step by step. We will start with the Roloc Pond structural components and functionality. We will then review the sequential steps of the design flowchart. We will understand the core principles and assumptions behind the structural calculations. And we will review the tools that engineers are offered to further understand and calculate their Roloc Pond project, like the worked example and the Roloc Pond calculation spreadsheet tool. In Chapter 1 of this tutorial series, we had the chance to understand the importance of the clay 5 brick, its reliable production size and compressive strength. Furthermore, we understood how this specific bond is formed and how the cavity occurs within the masonry, thanks to the specific brick layout and orientation. We mentioned the anti-seismic properties of the Roloc Pond technology, and this being true despite the apparent absence of typical columns and beam structures. The reinforced concrete frame is concealed within the walls, exploiting the cavities we just mentioned. The result is a compound structure that can withstand both the vertical loads through the load-bearing walls and the shear forces of the seismic event through the reinforced concrete three-dimensional frame. The result is a three-dimensional reinforced concrete truss embedded and perfectly bonded to the brick masonry. In order to start the project structural design, the engineer is guided through the sequential process outlined in the Roloc Pond design flowchart. The starting point is receiving the plans and elevation from the architect and beginning to compare the design features against the dimensional requirements outlined in the guidance document. And through the use of the available global analysis tool and following the intuitive steps, the structural design is brought to completion. Eurocodes have been the primary reference framework when developing the structural guidance document. As for the material properties, a list of assumed values is available within the Structural Design Principles manual. The design tool requires the reinforced wall junctions to be continuous over the height of the building. This frees up the central portion of the short elevations, where the placement of openings is left at the discretion of the designer, with of course some good practice principles to be kept into consideration. The main horizontal reinforcements are placed in suitable cavities and vertically spaced no more than 60 cm from each other. The main vertical reinforcements, instead, should be arranged at both free edges of every element, at every intersection, and within the wall, in order not to exceed a spacing of 5 meters between such reinforcements. The design tool provided has been developed to facilitate the design of relatively simple buildings, with an arrangement based on what may be expected of terrace low-rise affordable housing. In order to reduce complexity, the design tool has been developed with certain limitations, like a maximum of 3 stories, the shape of the building, and the design of single units with floor and roof structures spanning across the shorter direction. We encourage the viewer to further investigate these limitations in the second chapter of the Roloc Pond manual available in the SCAT Resources website www.madeingreatlakes.com. According to the Global Earthquake Model and the Rwandan Building Code, Rwanda is located in an area of moderate seismic activity. When establishing the project design ground acceleration, the engineer will select the most suitable model that combines the type 1 or 2 elastic response spectra, the local soil conditions, as well as ductility factors to determine the adequate multipliers to the peak ground acceleration. The equivalent static force, or ESF method, is a simplified analysis technique to substitute the effect of dynamic loading of an expected earthquake by a static force distributed laterally on the structure. The ESF method has been adopted in the design tools provided, in order to minimize the necessity for a structural analysis software. The ESF follows key indicators such as a rectangular building footprint, the building should be featuring a flat and uniform foundation level, re-entrant corners should be avoided, and lateral stability elements should be continuous through the building and more. When applying the ESF method, the total base shear is calculated by multiplying the mass of the building by the design seismic acceleration. This force is then distributed over the height of the building and horizontally in two orthogonal directions. This method is reliant on several assumptions, among which floors being flexible diaphragms. A flexible diaphragm can be considered as a simply supported beam spanning between two stability elements. Loads are distributed based on tributary widths, with half of each span going to one support and the other half to another. Vertical loads are generally beneficial to masonry structures resisting lateral forces. Vertical loads include the self-weight of the wall itself, as well as load from any horizontal structures which are supported onto the wall. This design approach proposes a reinforced shear wall system, theorized to perform as a braced bay, where a compression strut forms within the masonry along the diagonal of the wall panel. Vertical reinforcements form both a tie-down bar, resisting tension, and a reinforced masonry pier, resisting compression. The horizontal reinforcement resolves the thrust of the compression strut at each level and ties the bay together. In order for the shear wall solution to perform correctly, the minimum length of the shear wall between two openings, or between one opening and a corner, should range between 1 and 2.2 meters according to the height of the building. Where large openings exist in a wall at the ground floor level, the wall is theorized to perform as a moment frame system, where the more heavily reinforced wall junctions perform as columns, and the reinforced spandrel panel acts as a connecting beam. When a number of units exist in a row without seismic joints, all units can be considered to act as single structure. There are three types of column elements: L-junctions, T-junctions, and rectangular, in addition to the spandrel panel, which runs horizontally between openings at the level above and below. In order to establish design forces acting to the individual element, the moment frame must be modeled as a 2D frame in a suitable structural analysis software, such as Autodesk Robot or similar, using the outputs from the global analysis spreadsheet. More about this spreadsheet later in this video. A series of moment force charts have been developed for each of the element types. The combined major axis bending moments and axial compression forces are plotted on the relevant graphs to ensure they fall within the expected capacity envelope. Each moment force chart includes three different curves envelopes, which have been calculated based on different reinforcements bars, B8, B10 or B12, included in the vertical concrete pockets of each element. These different curves are used to select the reinforcement requirements for each member. The design tools provided with this document have been produced to ease the design process for simple, rectangular, low-rise buildings. However, the design methods included here, shear wall and moment frame approaches, may be applied to structural elements occurring in more complex structures. In this case, the engineer should consider the appropriate analysis method and may need to revert to the use of response spectrum analysis methods using appropriate analysis software. Combining the Scott roll-up system with other structural materials and elements may also be an option, for example, combining the masonry with a reinforced concrete frame to achieve a taller building. The second chapter of the Roll-up Construction Manual, Structural Design Principles, includes a fully worked example that engineers can refer to as a practical application of the structural design procedures explained so far. Among the tools provided, the Global Analysis and Shear Wall Calculations Excel file is a fundamental tool for a comprehensive roll-up structural calculation for buildings up to 3 stories. We encourage the viewer to download the Global Analysis tool and all the other documents mentioned in this tutorial on the Scott Resources website www.madeingreatlakes.com. Thank you.